Hello everyone, we continue the structure-activity relationship studies of beta-lactam antibiotics and we are talking about penicillins. We have already seen the essential features and in this video we will talk about the variables and how they affect the action of the penicillins. The learning objectives include here to identify the groups that impart acid stability to the drug and make them orally active, importance of the bulky groups if they are attached, and how their ability to hinder binding of the drug to enzyme, correlate the variable groups and their ability to enhance the spectrum of activity from narrow to broad, and also the stability of penicillins. As we have already said in the last video about SAR of penicillins, the SAR of penicillins contains of the pharmacophore, the variables and the stereochemistry. Today we will be talking about the variables. We have already seen this, that what are the essential requirements of penicillins. So we have said that apart from this R, almost everything is essential to the structure of penicillins. That means nothing can be changed. Okay. So now what is our main aim? Our main aim, as we have seen in essential, is target binding, and that target is transpeptidase. If drug binds to transpeptidase, drug is active. But other factors that are important include acid stability. If the penicillins get degraded before getting absorbed, or they do not get absorbed, drug is orally inactive. Or if the drug goes and binds to some other enzyme, in this case maybe beta-lactamase, that is called as non-target binding. Again the drug is inactive. And the spectrum of activity, we will always want the drug shows action against a wide range of microorganisms, in this case wide range of bacteria, the gram-positive as well as the gram-negative. So we can have narrow spectrum antibiotics which act against either gram-positive or gram-negative. Usually penicillins act more against gram-positive. Or we can have a broad spectrum where they act against both gram-positive and gram-negative, or they can even have an extended spectrum where some of them have good action on selected bacteria that are not susceptible to the above two classes. So this is the general structure that we have seen, and what we want to see here is how can we modify this R. Now if you see, if I attach this R with a benzyl group, this is the benzyl group. So what happens is, this drug will remain acid unstable, will have an intermediate spectrum, and is also beta-lactamase sensitive. Now why does it do this? This drug is called as benzyl penicillin, or also known as penicillin G. The unpaired electrons here in this O will attack this carbonyl in acidic environment, and thereby causing the breaking of the lactam ring, and thus we'll have an orally inactive drug. Also, because it cannot prevent the attack by beta-lactamase, then again it is an inactive. So it is beta-lactamase sensitive, it is acid unstable, can only be given parenterally, and it has a very good action actually, but known as intermediate spectrum of action. So to solve this problem, what we can do is, we try to decrease the density of electron at this carbonyl, which will then not attack this carbon. So what we do is, we put an phenoxymethyl group. So a phenoxy group is an electron withdrawing. So what does it do is, this drug has an ability, this group has an ability in fact to act in two ways. One is, this phenoxy group will withdraw in electrons through induction from the methylene group, as well as it will donate electrons through resonance to the phenyl group here, thereby decreasing the electron. In both cases it will decrease the density of electron here, and therefore will have a drug which is orally active. So you see that both this benzyl penicillin, the last drug, and this drug has the same spectrum of activity, but one is orally active, the other is not. But still these two drugs are not are still beta-lactamase sensitive. So to improve upon the action of drugs, that is, we want them to be beta-lactamase resistant, what we try to do is we try to put some bulky groups. Those bulky groups should not allow the serine hydroxyl to attack this carbon. That means this bulky group will somehow try to shield this carbon, right? Now this bulky group should not be very big, otherwise it may also shield the serine this carbonate from the serine hydroxide of the transpeptidase, which we want them to bind, right? That is the target site. So therefore there are selected bulky groups which will help here. So this is a steric shield. This drug is methicillin. It is acid unstable because there is no electron withdrawing group. It has a parenteral action. It has a narrow spectrum, but it is beta-lactamase resistant. Same case with nafcillin, which is also having this steric shield, and this drug is also having the same kind of activity, although it is slightly more orally active as compared to the methicillin. Next in this category of beta-lactamase resistant drugs is oxacillin. Now this compound heterocyclic ring, when it is having substitution at 3 and 5 position, this will again cause steric hindrance and therefore protect it from beta-lactamase. Also this oxazole ring has an electron withdrawing capacity, so it will also be orally active, that is acid stable. So this is acid stable, orally active, and narrow spectrum. So all these drugs are known as oxazoline penicillins because it contains isoxazole ring, oxazolyl penicillins. This is cloxacillin with the same actions, and this is dicloxacillin, also having the same kind of actions, only increase of potency in one of these cases. Then we have a group of penicillins which are very important, that is known as aminopenicillins, because at the alpha carbon here there is a group which is an amino group. This is a polar group which allows this drug called as ampicillin to have a hydrophilic character, thereby allowing it to go through these porine channels into the gram-negative bacteria. Also there has been reports that this ampicillin and amoxicillin are also absorbed by carrier proteins, therefore their plasma protein blood concentrations is quite high. This is a very good drug. It has a broad spectrum, and it also has an electron withdrawing amino group, therefore it is also acid stable, and it is beta-lactamase sensitive. The next drug is where you add an hydroxyl group at the para position to ampicillin, and what you get is an amoxicillin. This drug is much better absorbed as compared to ampicillin, has the same properties of ampicillin, and it can be easily given along with food. It causes less of diarrhea, which is a problem with ampicillin. Again, it is a broad spectrum electron withdrawing amino group, therefore it is also acid stable, but it is beta-lactamase sensitive because it does not have that steric hindering groups or bulky groups. Continuing with the alpha polar groups, we have again a new set of penicillins which are called as carboxyl penicillins because it has a carboxy group. Now this carboxy group is having better action as compared to aminopenicillins, but it has a problem. This compound is carbonicillin. Now if you see inside the body, this carboxyl group can undergo decarboxylation. That means removal of this carboxyl group, and if it undergoes decarboxylation, it becomes benzyl penicillin. So benzyl penicillin has good activity, but this had much better activity. But because of this decarboxylation, it will have the same activity, or you can say a degradation of the activity that is expected. It will show activity same as compared to benzyl penicillin, but not good as carbenicillin. This is a broad spectrum antibiotic, carboxyl group removal, therefore acid unstable, and it is beta-lactamase sensitive. Another drug in this group of carboxyl penicillins is T-Carr Saline, where we have a thiophene ring attached instead of an benzene. This drug is having an extended spectrum because it can act against more bacteria as compared to the other drugs, some specific bacteria, and therefore it is better to use these drugs. Another group of penicillin antibiotics includes the uridopenicillins, where you have an urea structure. So at the alpha carbon again you have an urea structure, whereby this drug known as piperacillin is a uridopenicillin, again having a very good activity, also acting against some specific bacteria, and therefore also called as extended spectrum penicillins. Same is the case with meslocillin, again a uridopenicillin having an extended spectrum and a broad spectrum as well. So what we have studied here is the substitution at R. The variables includes aromatic and heteroaromatic group, which could increase the gram-positive activity. Benzyl group shows good action, but it is acid unstable. Electron withdrawing groups increase acid stability. Bulky groups provide steric hindrance and therefore a beta-lactamase stable drug. Substitution at C-alpha with hydrophilic groups like NH2-COH groups give broad spectrum penicillins and some extended spectrum penicillins. This includes the aminopenicillins, the carboxypenicillins, and the uridopenicillins. What is important to note here is wherever there is an alpha carbon containing penicillin, all of them have been found to be beta-lactamase sensitive. And usually where you do not have this, it is more the groups attached to R are therefore acting mostly as steric hindrance, because you will find that there are some groups which are attached to these where they sterically hinder the approach of beta-lactamase serine hydroxyl to the penicillin lactam ring. So these are the references that we have used for this structure activity relationship studies. Thank you very much.